Imagine you generate this stunning photorealistic 3D model of a chair from just a simple text prompt. It looks totally flawless.
Right, visually perfect.
Yeah, exactly. But the second you drop it into a robotic simulation and ask a virtual robot to sit on it, the physics engine just crashes. Or, the robot falls straight through it like a ghost.
Like it doesn't even exist.
Exactly. Welcome to AI Paper Slop. Today's paper is called Embodied Gen V2, an Agentic simulation-ready 3D world engine for embodied AI, published by Horizon Robotics and Wooin AI. And we are just skipping the fluff and getting straight to the core insight today.
Yeah, let's dive right in. Because the primary bottleneck in robotics right now is that the current generation of 3D models, they just output visual shells.
Just pixels, basically.
Right. These meshes might look amazing on a screen, but for robot reinforcement learning, they're completely useless. I mean, they lack physical parameters, they have no collision meshes, and they offer zero interaction affordances.
You literally cannot train a physical agent on a purely visual asset.
No, you can't. And the solution presented in this paper is Embodied Gen V2. It's this end-to-end world engine that takes text or images and converts them into fully executable multi-simulator environments.
Which is huge. It leverages vision language models, or VLMs, combined with explicit physics validation, right?
Right, exactly. It automatically calculates and assigns mass, friction, and part-level graspability to generated objects. So it transforms them from this sort of visual slop into verifiable simulation assets.
And the return on investment here for the listener is it's massive. We're talking massive zero-shot sim-to-real transfer.
Oh, totally. By fine-tuning vision language action models entirely inside these generated scenes, the researchers raised real-world physical robot task success from a baseline of 21.7% to an incredible 75.0%.
Wow. From 21 to 75.
Yeah, it completely rewrites how we can supply high-fidelity data to embodied agents.
Okay, let's pull this apart, starting with that fundamental bottleneck.
Yeah.
Making a single generated object actually function inside a physics engine. Because I've always looked at the outputs of standard text-to-3D models as, like, Hollywood movie props.
Oh, that's a great analogy.
Right, like they're meant to look good from a specific camera angle. But if a robot actually tries to lean on one, the illusion just breaks.
It shatters, yeah.
So beyond just lacking mass, what is actually happening geometrically that makes these models crash engines like MuJoCo or Isaac Sim?
Well, generative 3D models operate in this normalized coordinate space, meaning they prioritize pixel-level appearance over geometric truth.
Okay.
This results in what we call non-manifold geometry. Think of it like those Escher-style impossible shapes.
Oh, right, the stairs that go nowhere?
Exactly. You get surfaces that intersect themselves, or polygons that don't fully enclose a volume, or edges shared by more than two faces.
Basically mathematical nightmares for a physics engine.
Total nightmares. When a rigid body physics engine attempts to calculate a collision vector against a shape that is, mathematically open or self-intersecting, it just cannot resolve the collision normal.
The math fails.
Math completely fails, and the simulator throws a fatal error.
So Embodied Gen V2 builds a pipeline to fix those Hollywood prompts. It starts by taking text or an image and feeding it through pluggable base models. And they specifically test it with architectures like Trellis, SAM3D, and Hunyuan 3D.
Right, they tested a few.
But if you pass in a 2D image of, say, a coffee mug, half of that mug is occluded in the image, obviously.
Of course.
So how does the system handle an image of a partially hidden object without just blindly hallucinating a random handle on the back?
Well, this is critical because occlusion is the default state in real-world deployments. To resolve it, the pipeline introduces a module called 3D Fixer.
3D Fixer, okay.
Yeah, and rather than discarding the partial data and asking a generative model to just guess a whole new object, 3D Fixer performs course-defined in-place completion.
In-place completion, so it keeps what it can see.
Exactly. It takes the visible, fragmented point cloud from the image and treats it as a rigid spatial anchor.
Ah, I see.
Then it conditions a frozen trellis backbone using occlusion-robust feature alignment. So the diffusion model is mathematically constrained to preserve the exact physical geometry of the visible anchor.
Oh, wow. So it only synthesizes the missing back half to logically complete the volume?
Right. You get a whole object without sacrificing the fidelity of your initial real-world observation.
That is super smart. So once that raw enclosed mesh is generated, we have to bridge the gap between visual usability and simulation usability.
Yeah, because it's still just a shape at that point.
Right. So the pipeline runs topological repair, it simplifies the mesh, and explicitly bakes the textures. But the unsung hero of this entire first stage seems to be the COACD algorithm.
Oh, COACD is huge.
The approximate convex decomposition. For the ML engineer listening who might not spend their days writing raw graphics code, why is this decomposition step so critical?
COACD is basically the gateway to functional simulation. Physics simulators absolutely choke on complex, concave surfaces.
Like the inside of a ball.
Exactly. Calculating collision dynamics across thousands of inward curving polygons is just computationally prohibitive. It leads to those jittery, unstable contacts where objects just vibrate endlessly on a table.
I've all seen those physics glitches in games.
Oh, exactly. So COACD mathematically fractures that complex, non-convex shape into a tightly packed cluster of simple, convex geometric primitives.
Okay.
And a simulator can calculate collisions between convex hulls incredibly fast.
And the performance metrics tied to that step in the paper are just staggering. Without COACD, a simulator operates directly on the raw surfaces. The collision success rate drops, and the collision mesh size inflates from a highly efficient 0.29 megabytes all the way up to 1.45 megabytes.
What's it bloat?
And it gets worse. If a user decides to skip the mesh fixing step entirely, the visual mesh size explodes to over 50 megabytes per object,
Right.
multiplying processing time by 8.
And if you scale that up to a training environment, skipping decomposition means you physically cannot batch load hundreds of diverse objects onto your GPU for parallel reinforcement learning.
You would just exhaust your VRAM instantly.
Instantly. And it goes beyond optimizing geometry, too. The pipeline then uses a VLM to analyze multi-view renderings of the object to infer its real-world scale, its probable mass, and realistic friction coefficients.
Yeah, it infers the friction.
Yeah, and it takes all of those unified physical parameters and packages them into URDF, XML, and USD formats.
Which are effectively the standard robotic blueprints.
Mm.
A URDF file tells the simulation software exactly where the center of mass is, what the bounding box looks like, how the object should react to gravity.
It's the actual physics manifest.
Right. And the pipeline even supports soft body dynamics out of the box for engines like Genesis. You can prompt the system for a t-shirt, and it generates an asset that will physically drape over a robotic arm.
Without a human engineer ever manually writing soft body physics constraints.
That's crazy.
Yeah.
The asset generation alone is a massive leap. We move from generating pixels to generating verified physical blueprints.
Absolutely.
But, just because a robot's hand doesn't phase through a coffee mug anymore doesn't mean the robot actually knows what a handle is.
Right. The object is solid, but we have to bridge the gap between a geometric shape and a usable tool.
Exactly. Which brings us to the affordance auto-labeling phase. This moves the pipeline from pure geometry to interaction semantics.
Right, because a robotic manipulation policy relies on affordances. It needs to know precisely where on the object to make contact, what function that specific region supports, and how to actually execute a successful grasp.
So how does Embodied Gen V2 initiate this?
By running the mesh through P3SAM, which is this 3D segmentation model that chunks the mesh into functional parts.
Wait, I need to push back on their architectural choice here.
Yeah.
Because the paper states they put a VLM in the loop to merge these parts after P3SAM does its segmentation.
Yeah, they do.
But why incur the massive latency and compute cost of an expensive vision language model just to merge parts? If P3SAM is already doing 3D segmentation, isn't that just redundant processing?
It looks redundant on paper, for sure, but it addresses the fundamental difference between a geometric boundary and a true functional semantic unit.
Okay, unpack that for me.
P3SAM is looking for structural changes, right? So if you feed it a pair of over-ear headphones, P3SAM will likely segment the smooth plastic top curve and the textured, padded inner cushion as two entirely distinct geometric fragments.
Because structurally, there are different materials and shapes.
Exactly. But functionally, to a robotic gripper trying to pick up those headphones, that entire assembly is simply the headband.
I see.
So the VLM acts as a semantic reasoning engine. It evaluates the rendered masks and groups those geometrically distinct fragments into a single functional component that makes logical sense for interaction.
That makes perfect sense. The VLM translates structural geometry into actionable logic.
Right. And once it merges those units, it attaches highly structured attributes to them. It assigns a part name, a Boolean for graspability, specific grasp scenarios, and functional labels.
But a language model hallucinating a grasp tag isn't enough for rigid RL training, right? Like, we need proof it works.
Exactly, which is why the system enforces a strict physics validation step. Once the candidate grasps are generated, they're exported directly into the Sapien physics simulator.
Okay.
The system actually instantiates a virtual robotic gripper, attempts the specific grasp, and tries to lift the object against simulated gravity.
And they set incredibly strict physical tolerances for success here. If the object slips more than 5 centimeters within the gripper, or if it rotates more than 30 degrees during that simulated lift, the grasp is outright rejected and discarded.
It's ruthless.
Yeah, and the pipeline achieves a 50% affordance pass rate through this end-to-end process, and only takes about 94 seconds to fully auto-label a new asset.
This step completely closes the loop on object creation. We aren't just hoping the robot figures out how to hold the generated mesh. We are generating an actionable, mathematically verified simulation entity.
The robot's policy has access to validated interaction data before it ever encounters the object in the real world.
Precisely.
So, okay, we have these actionable, physically accurate objects. The next logical hurdle is placement.
Right, the environment.
Yeah. If we're trying to build highly diverse training worlds, how do we logically arrange these assets into an environment without forcing a human ML engineer to manually place every single spoon, plate, and table?
Well, the paper introduces this task-driven interactive worlds generation module. They use a large language model to ingest a natural language prompt, for instance. You say, put the broccoli on the dish, and the LLM parses that prompt into a highly structured scene graph.
I really appreciate the architecture of the scene graph because it categorizes everything into 5 distinct layers.
Yeah, it's very organized.
You've got the robot, the background, the context, which is usually the primary furniture, like a kitchen island, the manipulated objects, and distractors.
Right.
It reminds me of a digital green screen production. The system intelligently isolates the task-relevant interactive foreground objects from the static modular background.
That's a great way to think about it.
If the policy is just learning to manipulate broccoli on a plate, you aren't wasting immense compute power simulating complex physics for the walls and the floor.
Exactly. Decoupling the static environment from the dynamic task elements saves massive rendering and simulation overhead. Once the LLM structures that graph, the system deploys a spatial placement solver.
And how does that solver work?
It uses a breadth-first search, or BFS, approach to iterate through the objects. And as it places each asset, it runs intersection over union, or IOU checks.
Right, and for the listener visualizing this, IOU checks are basically testing the 3D bounding boxes of the objects to see how much they overlap.
Crucial step.
Because if you skip this, and 2 objects clip into each other on initialization, the physics engine tries to instantly resolve the overlapping matter, which usually results in the objects being violently ejected into the stratosphere the millisecond you hit play.
Yeah, they just explode outward. So the breadth-first search systematically respects those spatial constraints. It places the table, checks the space, places the plate, checks the overlap, and then places the broccoli.
Super methodical.
Right. And as a final stabilizing step, the system runs a brief gravity-settling pass inside Sapien. It lets physics take over for a few frames to resolve any flirting artifacts.
So things actually drop onto the table.
Yeah, dropping the objects naturally onto their supporting surfaces so the robot doesn't arrive in a world where the broccoli is hovering 2 inches above the plate.
That is so elegant. Now, generation speed is a major factor here. If you were doing fully online generation, meaning the system synthesizes every single mesh and texture from scratch, it takes about 47.7 minutes to build one complete world.
Which is a bit slow for mass scaling.
Right, but by utilizing offline asset retrieval, pulling from a pre-generated verified library, that time drops to just a few minutes. 83.3% of those generated worlds are perfectly usable without a single manual tweak.
And the architecture extends beyond tabletop manipulation as well. The researchers built a large-scale scenes generation module.
Right.
Because they cleanly decoupled the semantic reasoning of the LLM from the geometric solving of the placement engine, they can scale up to generate entire multi-room navigable floor plans.
Full houses.
Yeah, featuring controllable complexity tiers ranging from minimalist environments to highly cluttered detail environments, which is absolutely crucial for training mobile manipulation robots that have to navigate full-scale houses.
But let's look at the reality of ML workflows for a second, because even with an 83% success rate, a generated scene is rarely absolutely perfect for a specific edge case training run on the very first try.
Oh, for sure. You always need to tweak things.
Exactly. If you're an engineer and you want to swap a specific chair for a stool, or shift a table slightly to the left, having to regenerate the entire 47-minute scene from scratch is a massive, frustrating bottleneck.
Editability is the dividing line between a research toy and a production tool. If you cannot iteratively refine the simulation state, the whole workflow breaks down.
Right.
So Embodied Gen V2 addresses this by introducing a feature they call vibe coding.
Vibe coding, it's such a great term.
And it really is.
It's an iterative conversational interface for 3D world editing. But unlike earlier text-to-3D tools where you just, prompt a black box and cross your fingers, vibe coding revolves around a persistent world state.
That's the key.
The system continuously tracks the scene graph, the specific asset IDs, their 6 degrees of freedom spatial poses, and the full dialogue history.
And the underlying mechanism driving this vibe coding is what the authors call a parse, ground, invoke, commit loop.
Parse, ground, invoke, commit.
Yeah. When an engineer gives a natural language command, the LLM agent first parses the intent. Then it grounds that intent by mapping the language to specific node IDs in the scene graph. Next, it invokes deterministic skill backends to execute the change.
Can we break down that invoke step a bit more? How do these deterministic skill backends prevent the LLM from making a change that breaks all the physics we just spent so much time validating?
Well, think of the LLM as the creative programmer, loosely writing code based on a vibe saying, hey, let's add a dining table right next to the fridge.
Right.
But the skill harness acts as a strict, unforgiving compiler. Before any change is allowed, the harness runs physical and geometric checks. It calculates the bounding boxes and tests the placement in the simulator. So if adding that dining table causes a collision with the refrigerator door, the compiler throws an error. It intercepts the failure and returns a diagnostic error message back to the LLM for a retry or a fallback without ever executing the final commit phase.
So the existing world state is completely protected. That is massive. Because in older generative models, asking for a small tweak like, changing a cup's color, often caused the entire room's geometry to randomly regenerate, hallucinating new windows and deleting furniture.
Right, the infamous consistency problem.
But because of the parse, ground, invoke, commit loop, your edits are strictly bounded deltas. You are adjusting the simulation state with absolute precision without breaking the underlying physics logic.
That state protection transforms generative AI from a slot machine into a highly controlled engineering interface.
Okay, so we have built this incredible infrastructure. We can generate physically accurate assets with automatic affordances. We can arrange them into logical, task-driven worlds, and we can iteratively tweak those worlds using conversational vibe coding.
It's a massive stack.
But here's the ultimate test, the core validation for any ML engineer listening. Does any of this actually improve the model weights of a physical robot?
The downstream validation from the Choi et al. Study is what makes this paper a breakthrough.
Tell me about the numbers.
So the researchers took a pre-trained vision language action policy, or VLA, and fine-tuned it purely using environments generated by Embodied Gen V2. In simulation, the task success rate skyrocketed from a baseline of 9.7% all the way up to 79.8%.
Wow. A 70-point jump in simulation is massive.
Yeah.
But the scaling data is what really stood out to me in the paper.
Like scaling laws, yeah.
When they increased the number of generated training scenes from just 1 to 50, they shrank the performance gap between in-distribution and out-of-distribution tasks from a massive 41.1 percentage points down to an almost negligible 2.6 points.
Shrinking that generalization gap provides concrete proof that the diversity generated by this pipeline isn't just visual noise.
It's actual learning material.
Right. It is providing rich, actionable learning signals that force the policy to generalize. And the definitive proof is the sim-to-real transfer.
The real-world test.
Yeah. When they deployed this fine-tuned policy onto physical robots in the real world, task success jumped from 21.7% to 75.0%.
That is just incredible.
And even more importantly, dynamics failures, which are situations where the real-world robot misjudges the weight, friction, or physical behavior of an object, those plummeted from 66.7% down to 18.3%.
We have to contrast this with the historical approach of using hand-built scenes. The researchers tested a policy trained on SimplerNF, right?
Yeah, they did.
And SimplerNF is a collection of heavily engineered, pristine environments crafted manually by human developers.
Very labor-intensive.
Very. And that policy achieved 96.7% success on its own training environments. But the moment they transfer that policy into the embodied gen-generated scenes, the success rate completely collapsed to 36.0%.
It just couldn't handle the diversity.
It is incredibly ironic. I mean, for years, ML engineers treated handcrafted, beautifully designed digital environments as the absolute gold standard for reinforcement learning. But this paper proves that highly structured, diverse, generative slop actually forces the policy to learn vastly superior behaviors.
It exposes the inherent brittleness of manual scene authoring. A human engineer, no matter how dedicated, simply cannot manually randomize lighting conditions, complex textures, novel distractors, and object geometries at the massive scale a neural network requires to build true robustness.
It's just impossible.
Right. Generative infrastructure forces the model's policy to understand the underlying physics and functional semantics of the task, rather than just memorizing the layout of one pristine, static room. By coupling metric geometry, physical validity, interaction semantics, and cross-simulator portability into one shared representation, this pipeline establishes a true closed-loop learning environment.
It effectively transforms 3D generation from a visual novelty, those Hollywood props we started with, into a highly scalable, policy-ready simulation infrastructure. We are no longer just generating pretty pictures. We are synthesizing raw, verifiable experience for robotic brains.
And that verifiable experience is exactly what will unlock the next generation of general-purpose embodied AI. The data bottleneck is finally being cleared.
It really is a paradigm shift. And if you are listening to this and building robotic systems, I want to leave you with a thought to mull over, building directly on this idea of closed-loop learning.
Oh, this is fascinating to think about.
Right. Think about the potential for an auto-curriculum. If a system like Embodied Gen V2 can perfectly generate and validate physics-ready worlds purely from text and visual inputs, we are rapidly approaching a future where a robotic system observes its own failure in the real world.
So it generates its own training data based on where it failed.
Exactly. Imagine a warehouse robot dropping a specific, highly reflective type of coffee mug. It sends that failure data back to the server, and the AI automatically hallucinates 1,000 slightly varied training rooms targeting that exact lighting condition and grasp weakness.
Wow.
It fine-tunes the policy in simulation, tests it, and patches the physical robot overnight without a human engineer ever lifting a finger or manually tweaking a bounding box.
The training wheels never come off. The environment simply keeps evolving exactly as the agent needs it to.
It's an incredible future. Thank you for tuning in to AI Paper Slop and digging into the future of simulation with us. We'll catch you on the next one.